All right. I want to show you some slides regarding scintillation spectrometry. This is only brief introduction to the lab session. At first, let's look at the scintillation materials, then liquid scintillation spectrometry. This liquid scintillation spectrometry, as told by Aria yesterday, it can be used by using beta spectrometry, but also for alpha detection too. All right, let's start with the scintillation materials. I yesterday talked something about these things. So, ionizing radiation interaction with scintillation material, this leads to a flash of light in the scintillation material. So this light is not necessarily visible in the human eye. And as I explained yesterday, the light interacts with the photocathode, resulting the produce of electrons, and these electrons are multiplied in the photomultiplier tube. The point is that the light signal is proportional to the activity of the radionuclide present in the sample material. This is sometimes very useful, this thing. I mean, the duration of the signal is usually very short. This is sometimes quite good in coincidence spectrometry. Okay, and because the signal is very short, the time resolution is also very good, much better than MCA's multi-channel analysis usually, or hybrid germanium usually has. But the point is that the energy resolution is not necessarily very good. But it can be applied in certain applications. So the point is that efficiency is sometimes very good because you can use very large scintillation detectors in some cases. So, scintillation materials are used to detect alphas, betas, and gammas. Alpha particles can be detected, for example, by placing a very thin zinc sulfide layer on the sample, which produces light and it can be amplified. So, scintillation materials can be grouped as follows: inorganic or organic scintillants, or gaseous, solid state, or liquid scintillant. This is an example of a surface contamination monitor. This is the photomultiplier tube. This. So, regarding inorganic scintillants, perhaps sodium iodine detector is the most commonly used scintillant for detecting gamma rays. This scintillant is used for beta particles, and these are used, for example, for neutron imaging or contamination monitor. And compared to the organic scintillants, light output is higher, but the response is slower. Organic scintillants, it's a difficult thing. They are made compounds like plastics. The point is that the density at atomic numbers are lower compared to these, which means that they are not necessarily so efficient as inorganic scintillants. All right. This is a very short presentation. I am not expert in this area. However, if you ask me difficult questions, I hope that Aria or Parath will comment your questions. But these can detect low-range radiation like alphas and betas. If I understood it correctly, you are not using these spectrometers for alpha particles, only betas. All right. All right. So these are the nuclides that are usually analyzed by liquid scintillation method. You are mainly analyzing this. Do you analyze these? Tritium. Yeah. All right. So the point is also that the scintillation materials, they are selected based on the radionuclide to be analyzed. This is the quantulus system. Do you have this coincident dual photomultiplier? Yeah.
We have the same LSE.
Yeah. So, the point is that the sample is put into the scintillant material, and this is a good thing because it provides almost 4π geometry. So the efficiency is quite good for low energy photons or betas or alphas, because high energy gammas certainly escape from these small vials. So it's a cocktail, it's a mixture of solvent, surfactant and scintillators that produce light when excited by ionizing radiation. There are usually, or quite often, two different scintillants. First one releases the light and the second one enhances the signal. Do you use glass or plastic vials?
Yeah, polyethylene.
Yeah, all right. Yeah. So there is a quenching process which limits the applications. So the energy transfer from the decaying radionuclide, it is reduced or interrupted, leading to the decrease of produced photons. And this quenching process must be taken into account. There are at least two main processes. There are some others, I think, chemical quenching or color quenching. Are there some others too? Yeah. So this reduces total light output and shifts the pulse height spectrum towards lower energies. And this might reduce the counting efficiency too. Commercial systems are often operating in so-called coincidence mode, which means that the pulse is only registered if two photomultiplier tubes record the same pulse within the short time period. This improves the accuracy and reliability of the measurements. For example, reducing the background noise or spurious signals. So you can detect alphas if you utilize pulse shape analysis. So it's possible to distinguish signals from alphas and betas. So these are alpha signals here. These are signals for betas. So alphas produce shorter and more intense light pulses, whereas pulses from betas, they are longer and less intense. There are ways to determine the so-called PSA level by using, for example, standard samples such as this nuclide or this nuclide. Only these two. But what is the reason why you are not using alpha detection in?
Alpha spectrometry and HPG for the gamma.
Yeah, all right.
Basically,
So whichever is not possible for using HPG
Yeah.
and alpha spectrometry,
Yeah,
you do it.
and that is a laborious process.
yeah, yeah.
For liquid
Yeah,
simulation,
it is, yeah.
Again, the cocktails are
That's scintillator.
scintillator cocktails are quite expensive.
Yeah, yeah,
So
they are.
in order to analyze polonium,
Yeah,
if you use the digestion method,
Yeah.
it is not that costly. But if you have to use the liquid scintillation counter,
Yeah.
then
very expensive.
it is very expensive.
yeah, yeah. I think we have 3 or 4 of these Quantulus systems in my laboratory, as you saw in the video. We are routinely analyzing polonium, for example.
So I had a question. If you are analyzing alpha using liquid scintillation counters, wouldn't there be a problem of attenuation due to the vials? Because alphas are not that penetrative enough.
Well, you can ask Aria.
Vials, but you are changing the vial.
The plastic might attenuate.
Yeah, but we are not reusing that.
Hmm.
For each sample, you have to use the new one.
No, no.
Okay.
Plastic might attenuate the polonium, right? So I don't know how you use.
I don't have special experience in
No,
this
we can skip
area.
the question.
Yeah.
For the next one.
Yeah, all right. So, about the scintillation spectrum analysis, I mean that I would like to compare. I'm not considering here not liquid scintillation systems, only those solid systems. So basically, the spectrum analysis is same for high purity germanium. There are no big differences, except, of course, the resolution, which is not very good. For example, in sodium iodine detectors, the resolution is 7 to 9% or something like that. So, and resolution is calculated like this. So it's a big difference, so energy difference of the left side and right side divided by the energy. And the problem is that peak overlapping may be notable. So there is comparison for iodine, sodium iodine and high purity germanium. So there is a big difference in resolution. I think using scintillation materials is a very good system in those cases when you detect, for example, only one nuclide such as cesium-137. And there are different types of materials. I think this is bismuth germanium oxygen material, this one. This is lanthanum bromide. The resolution is very good in that type of the scintillator. But these are quite expensive, these lanthanum bromide detectors, compared to the sodium iodine detectors. This is one example. Basically, detection system is like high purity germanium. You can have a lead shield here, you can put the sample here, and this kind of system can be used in the field measurements. But then you have to take into account that if temperature varies a lot, which is not a problem here, but a problem in Finland, if we want to measure or use this system during winter time or summertime. All right, this is the energy calibration curve, which is quite linear in case of sodium iodine. This is one example of sodium iodine spectrum for cobalt 60. There are same kind of peaks as in high resolution gamma ray spectrometry. One of you asked me why there is only one backscatter peak when there are two gamma peaks. But the point is that backscattering peak is not very much it doesn't depend very much on the energy. It depends a little bit, but not very much. That's why this peak is more wide. All right, I think, okay, this is almost the final slide. So I didn't look through this paper, but perhaps you might look through, because they say that there are some new ways to do scintillation spectrometry for environmental sample measurements. I think this is my last slide. So, advantage of scintillation spectrometers is that they are or can be very large. I remember that Finnish Geological Institute used very big scintillation detector after the Chernobyl accident. They put that detector in an airplane and use very low altitudes, 100 meters or so. The detector size was indeed very big, and the resolution is very bad. But they just wanted to produce a fallout map in Finland, mainly from cesium-137. So, advantages of cesium is that they are cheaper compared to high purity germanium by a factor of at least 10, at least. They are appropriate in field measurements. You cannot carry heavy lead shields out of the laboratory. They need low power, no cooling. Maintenance is simple, relatively simple. application areas are quite wide. They can be well suited, for example, in security systems such as portal monitors like this one here. And once more, the efficiency is good. For example, these are the portal monitors looking for this big truck here. All right, this is it. No more.